It is always a good starting point to catalog all the symmetry elements that belong to a molecule, but we need to take a step further and think about the operations that those symmetry elements imply. So I'm going to divide our discussion in this area into two. One, talk about the rotations, both proper and improper, and another to talk about the reflections. So as we talk about the rotations, I want to look at, for example, a C3 axis in a molecule. Now that C3 axis can generate a couple of different types of symmetry operations. For example, I could operate that C3 operation once, or I could do it twice. And what does that correspond to? Well, if I think about rotation of some vector in a plane, all right, if I rotate this once through a C3 operation, I would get to here. If I operated a second time through a C3 operation, I might get to here, and a third time would bring me back to the starting point. So if I were to go ahead and fill out the third one of these C3 operations, in fact, this operation is equivalent to the identity operation because I've simply returned the molecule back to its starting point. So that means that this C3 axis actually gives rise to two operations, one of which corresponds to applying the C3 operation once and the other to twice. Now, if you're wondering why not consider this to be the negative, well, this in fact is the same as going C3 minus 1. Right, that would be going this direction back to C3. So we could partition them that way, and that's, I think, what happens on the Otterbein symmetry site. But I'm going to go with this particular type of notation. So, for example, that means that for a Cn axis as a symmetry element, I should give rise to n minus 1 equivalent operations, or essentially related operations, that relate to operation of Cn some number of times. All right, all of these operations, though, take me to equivalent configurations of the molecule, but they're all related. They're all related to the same rotation axis. So I'm going to say that all of these operations, all of these n-1 operations, belong together to something I'll call a class. They are a class of operations that relate to a rotation through an angle of 2n minus 2 pi over n around the axis of rotation, around the symmetry element. Now I'll have a similar sort of situation for the improper axes, but there I'm going to do a rotation and then I'm going to reflect in a plane perpendicular to this. So for example, if I have a plane drawn here and the improper rotation axis perpendicular to that plane, if I start up here and I do a rotation down to here, I'll then do a reflection across, so my product vector will be something that sits out here. All right, I'll have to do a second operation of S sub n to bring it back to the same side of the plane. So for that reason, let's say, for example, I have an S3 symmetry axis. Okay, in that case, I'll have symmetry operations that correspond to S3 once. That'll get me to the left-hand side of the plane. S3 twice, which will bring me back to the right-hand side of the plane. So this is equivalent to C3 twice. I'll have S3 three times. What would that correspond to? Well, I will have gone all the way around, and then I will have, S3 three times, I would have gone all the way around and then reflected across to the other side. Well, that's just a reflection, so this is a reflection. I'll have S3 to the fourth. That'll correspond to C3 used 4 times, but that is equivalent to C3 operated once. I'll have S3 to the fifth, and this will now correspond to having done C3 twice and then reflected. And I'll have S3 to the sixth. All right. Now at this point, I will have gone twice around my rotation, and I will have reflected an even number of times across the plane, so I would be back to my identity operation. So the only ones that are really different from other designations are this one and this one. And that's generally going to be true of all improper rotations that have an odd number. If an improper rotation has an even number, however, so if I have an S4 improper rotation axis, like the one we saw in octatetrene, what sort of operations will I get from that? Well, I'll have S4 operated once. That takes me to the left-hand side of the plane. I'll have S4 operated twice, all right, which is equivalent to a C2 operation. I'll have S4 operated 3 times, and I'll have S4 operated 4 times, which is equivalent to getting back to my starting point. So again, I will give rise to 2 different new operators plus one that is equivalent to a C2 type operation. So I have to be very careful in how I count the number of operations that arise from an improper rotation axis versus one that comes from a proper rotation axis. Now let's take a look at reflection. In the case of reflection, oftentimes we're not going to have reflection unless we also have a principal axis of rotation. So I'm going to assume that we have a principal axis. I'll call it C sub n. And that principal axis I'm going to orient like this. All right, now the reflection can involve a plane that's oriented in various ways relative to this axis. For example, let's suppose that I have a molecule where my CN axis divides n equivalent points that are arrayed in a circle perpendicular to that axis. All right, so each of those points that are part of determining that symmetry will contain a plane that goes through them. So these 2 points are the ones that I'm trying to put that plane through, and a plane that contains the CN axis. Whenever I have that, I call the plane sigma sub v. The v stands for vertical. It is a vertical plane that contains the principal axis. All right, now what if I have a plane, though, that is perpendicular to my principal axis? So in other words, here is my principal axis, and my plane cuts across it like this. In this case, I'm going to have a plane that I call sigma h, where the h basically stands for horizontal. All right, so my horizontal plane in this case could contain the molecule. If the molecule, like benzene, has a principal axis that runs perpendicular to the plane of the molecule, or it could just be a plane that marks a symmetry within the molecule. There's a third kind of reflection plane, though, that I can see, and that is if I have a series of points like I've drawn here, where these points basically define an Enfold symmetry that is somehow aligned perpendicular to the CN axis. If I should have a plane that cuts directly in between 2 of these points, so in other words, it's bisecting the line between 2 of these points, I would have a special designation for that plane. It contains the CN axis, but I'll call it a sigma sub d, or dihedral reflection plane. And so you will see this in some molecules that you'll examine during the course of this lesson and the course of this module. All right, now the reason why we're worried about this number of operations is that the number of operations itself is a number that we need to pay attention to. The number of symmetry operations we're going to set equal to a number that we'll call h, and that h stands for the order of the symmetry. So in other words, the total number of symmetry operations, h, is going to be the order of that operation, and it turns out there's going to be other things related to that order that we'll need to pay attention to. So this has just been a brief introduction into how we relate symmetry elements and operations, but you'll need to do some careful reading and thinking as you go through this material so that you get it down get it down pat.